very brief history on myself. I'm an organic chemist by training. I have a little bit of knowledge in biotransformation. I've been with GSK now for 17 years as a process chemist. My current role is part of what we call the synthetic biochemistry team. And we very much see biocatalysis, biotransformations, synthetic biology as a key component of our aspirations around sustainability. So I also sit on the green chemistry panel as well within GSK. So moving straight on to the work package, there are 5 work packages. Work package 1 is the smallest one. We have a very good understanding within our individual companies of where we are and what needs to be done. There was a paper published in 2007 where several pharma companies got together, listed out the different reaction types which were ongoing within their companies, and that enabled a snapshot of the different reactions and an understanding of really in terms of number of reactions or difficulty of those reactions, which were most non-green, i.e. where we should actually focus our efforts. So this first proposal is really about updating that, bringing us bang up to date. This paper is 4 years old. Really what this is about is really covering where we are in the world today with respect to scarcity of certain metals. So I hope everyone is aware that 50 years from now we're going to have problems unless we start thinking about this now. I'd ask for a poll of anybody in this room who doesn't own a mobile phone. Nobody. The rare metals you use in your mobile phone are the rare metals we actually use to make our pharmaceuticals. As those metals run out, are we going to continue making mobile phones, or should we make medicines for people to live longer, feel better? It really does start to become as stark as that if we don't actually start thinking about these issues now. So we need to think about metals as catalysts. We need to think about those transformations which have particularly poor green metrics, mass efficiency. We really need to think very, very carefully about those transformations which could actually benefit by using lower volumes of solvent or more benign solvents. And again, what the previous paper didn't really cover is the potential impact of synthetic biology and what those methodologies and targets could impact. Likewise, as Philippe touched on, was flow chemistry or continuous chemistry. The next package, as you can see, is the term catalysis and flow chemistry. Really, this is very much about developing more sustainable methods for making the kind of complex molecules we see in the pharma industry. This is about organic and organometallic catalysts, potentially in combination. We want to really see the amount of catalysts being used minimized by first intent. We also need to think that we have to be realistic. We have to think about recovering those catalysts and leakage. And this is particularly true for organometallics, of course. We need to think more about continuous and flow chemistry. In parts of the larger chemical industry, this is far more prevalent than we see in the pharma industry. We've been a bit slow to uptake on this. But these kinds of chemistry actually enable certain methodologies which are just not safe to do in a batch process. So this is something we really need to think about. And of course, not only that, but these kind of technologies do allow you to run more concentrated chemistry. So again, there are obvious advantages to doing this. And you know, the use of microreactors, and the point that Philippe very well made there, if you haven't got access to a microreactor, you don't think about this sort of chemistry. The second package, biocatalysis. Clearly, when you actually look at the metrics in the literature of biocatalysis, which is used in academic or industrial settings, you find that this is actually a very effective green tool. There are some problems. So first, there's really not a great range of enzymes which are commercially available. And those which are available, you typically find that the substrate range is not that great. This is an area where we really need to improve. If we want this to be a general technology, we need a greater range of enzymes. We need to get better at designing and developing new enzymes using genetic engineering. And the tools to actually do this have moved on leaps and bounds in just the last 5 years. Some of the processes which used modified enzymes just a few years ago, what took entire teams the best part of a year to do can now be done by single researchers in a few weeks. The science has moved forward dramatically, but a lot of people aren't really aware of what can be done. We need to make a difference using this science. Some of the enzyme types which industry feels we really need to think about. So one of the most common and easiest transformations for a chemist is to go from an ester to an amide.